Okay, we'll start with linear regression. So we will basically look into, so all we have looked into is machine learning and the real world application of machine learning and types of machine learning, right? And with that, we will move on to our next section, which is linear regression. So let's talk about what is a supervised learning. Now, when we look into supervised learning, it means that there is someone who will tell us, what should be the output, or rather there is a supervision. Okay. Now, when we train a machine learning algorithm, if we give the corresponding target or the corresponding label to that particular machine learning algorithm, that okay, it should either be pass or fail, or it should be 2, 3, and 4, or 5, 6, and 7. So this is called a supervised learning. Take it in a way where if I ask you a question and in Menti I give you 4 options, so you know that the answer is going to be any one of the 4 or any one of the 3, right? If there are 3 options. So supervised learning is a type of learning where you have a corresponding target, right? So every input or every question I ask you should have a answer out of the 4 or 3 or 1 or 2 or 10 options, right? So this is a supervised learning. Now, for example, look into this data set where it talks about, what is the year of registration of a particular car? What is the vehicle type? What is the mileage? What is the kilometer driven by that particular car? And, what is the brand and fuel type? So if you want to buy a second-hand car, you'll always look into these type of information, and based on that you will say that okay, I'm going to give you 2 lakh rupees or 3 lakh rupees. And so uh, the these are the factors which we look into, and this is the target which you will predict on your own. Say for example, you are an individual and you want to find out the price of this used car. Okay, and from your own guess you will probably say, right, it will be like 3 lakh rupees or 2 lakh rupees, right? All of these data which is present here, year of registration or vehicle type or mileage up until fuel type, are called the independent variables. They are independent, right? They are not dependent on anything. But this price which we are going to predict, right, it is a dependent variable because this is dependent on all these factors. Got it? So we have independent as well as dependent variables. This is independent and this is the dependent, right? Now from here you can, if I give you a sample data, which is the last one, you can obviously predict what is going to be the price using a machine learning model. And this is what we will look into with many such examples. Okay. Now, a supervised learning for price prediction of used cars will have independence and dependent variables. As I told you, right? These are the independent variables and this is the dependent variable, right? So this is also called predictor, right? And this is also called the outcome, right? You can say dependent variable or outcome. And here you can say predictor, right? Predictor or independent variables. Okay, predictor is written here. Now, what is regression, right? Regression is basically a type of algorithm, okay, which basically predicts the value of continuous dependent variable using independent explanatory variables. So it basically predicts continuous dependent variable. Now you know what is a continuous and a categorical value, right? Continuous and a discrete value, right? So continuous values are basically values which has certain numbers. For example, which are not in a range. For example, 20.5, 72, 96, 1005, right? So these are all continuous value. These are all continuous values. So regression basically predicts the values of continuous dependent variable. In the previous case, we have price. We all know that the price can be, say, 3 lakh, right? It can be 3.05 lakh, right? It can be 3.09 lakh. So this is actually a continuous dependent variable. Why continuous? Because you have values like 20.5 and 72 or 3 lakh, or does not have any range. A car can be from any value to any value, right? And it is dependent because we are predicting the outcome. Okay, outcome is always called a dependent variable, and we use an independent explanatory variable. Why it is called explanatory? Because we are able to explain about that particular car. See, we are able to explain about that car, whether it is Hyundai or Maruti or Honda, right? Whether it's a petrol or a diesel car, whether the mileage is 32 or 27. So we are able to explain that particular data set, right? Or particular car, for example. So regression is used to predict values of continuous dependent variable using independent explanatory variables. Okay, if you have any question, do let me know. Okay, please mute yourself, unmute yourself, or use the chat box. Right now, as I said, you can predict the price of a car using an independent variable mileage, right? So you can look into the mileage and you can say, right, that the mileage is very low. I am not going to pay much price for it. Obviously, if it is a high-end brand, the mileage will obviously be low, but you will make a comparison with the brand as well, right? Only with mileage, you will not be able to answer your question, whether the price of the car is, 3 lakh or 5 lakh or 10 lakh based on mileage. So this is one independent variable, but it's not enough to, predict the price of the car. And you can plot this over a graph. Say, for example, here, if I want to plot, and this is the mileage, and this is the price. So you can say this 10, 20, 30. So if you say if the mileage is 15, right? If it is 15, the price of the car is going to be, say, 3 lakh, right? So you have a point here. Just give me a second. Okay, sorry for that. Yeah, so from that you can say if the mileage is 15, your price is going to be 3 lakhs, right? If the mileage is, say, for example, 21, right? Your price is going to be 3.16 lakh. And this is how you'll plot all these points. You might have points everywhere. And we'll see how to create a regression line. So for now, we have used an independent variable mileage in order to predict the price of a car. Now, regression use cases can be anywhere. You can, use it. You can use it in a real estate case also. You can use it in a marketing, sales prediction as well. So model house prices as a function of home's living area, number of bedrooms, bathrooms, and lot size. So based on the 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 neighborhood, right? The number of bedrooms, the bathrooms, if schools are available or hospitals are available, the price of the real estate also changes, right? So we can predict the price of a particular house based on certain parameters, right? Some parameters are, what's mentioned here. It can be number of bedrooms or bathrooms or lot size, or how many parkings are available, and if there is a school in the nearby area, right? Next is marketing. We can model a relationship between online advertisement cost and monthly e-commerce sales. So if you have no sales at all for a particular product, you don't want to waste your advertisement cost. Rather, you have to change the model product or you have to find out other ways. So you have to find a relationship between online advertisement costs. So based on the sales of that particular product, you have to create a model that how much you are going to spend on that particular advertisement of the product, right? So this can be achieved through regression. Why? Because the end output is a number. You can say, for example, say I want to spend, dollar 5,000 on advertisement or 50,000 on advertisement based on how much monthly sales you have. How much monthly sales you have, based on that you will create a model which will tell you what should be the ideal cost of advertisement, right? Next, it can be used in medicine as well to forecast medical expenses for insured population based on attributes like age, gender, smoker, BMI, right? Companies basically, so if I enter certain details of my own, right, in a term insurance, say for example I'm buying a 1 crore rupees term insurance, and I have to and I entered all my details, my age, and whether I'm a smoker or a non-smoker, my gender, my BMI, everything, and it gave me, every year you should pay 17,000 every year. But if someone who is like 22 or 23, if he fills this form, and it will probably generate something like 15.5K, right? And then the end output is a number. So that's why we are using a regression case here. So in medicine or in insurance, we use this forecasting model just to find out the expenses. Next is model relationship between the crop yield based on amount of rainfall. So it will tell you how much rain is going to happen, and how much crop is we are going to yield, right? And this is type of prediction which a lot of FMCG companies also do when they hedge crops with farmers. Next is introduction to linear regression. Now, as we know that uh, relationship or linear regression is basically a relation between the dependent and the independent variable. We have all seen what is a dependent and independent variable. The one which we are going to predict is called a dependent, and the ones which helps us to predict is called the independent. So here price is independent variable, and for example year of registration is a independent variable. And linear regression, why it is called linear? Because the relationship between the x and the y, say for example if it's y, if this is x, so the relation between the x and y is always linear. You can see, you can draw a line passing through the points. Okay, that is why it is called a linear regression. Now we'll look into what makes linear regression popular, right? Linear regression is so popular because it is very easy to implement. Okay, we'll see how to implement linear regression. It is very powerful. Okay, a lot of time series analysis is done on linear regression. Even if you learn advanced deep learning models, you will see the background of it is linear regression. So if you don't understand linear regression, you'll will not be able to understand state of the art models where we are using neural networks, right? The background of it is linear regression and gradient descent algorithms. Next is it is very easily scalable, so you can scale the model very easily. So that's not a problem. If you are performing this task for 10,000 data points, if you want to scale this to 1,000,000 data points, not a problem. Okay, so linear regression is very scalable. Now, how linear regression works? So let's look into something called calculation of the dependent variable using independent variable. So the question is, what is the price of a car when the mileage is 27 kilometer per liter, right? And for that, what we will do, we will plot um, a graph between mileage and price. We will plot a diagram between mileage and price. So if the mileage is, say for example 20, right, our car price is somewhere around 1.9 lakhs. If the mileage is 23.24, right? The price is say 2,50,000 or 2,30,000, for example. And as in when the mileage increases, the price of the used car is also increasing, because we obviously know that the better the mileage, we are going to pay more for that, provided that is of the same brand and then same company. Okay, so only one mileage is the independent variable here. Now with this, you can plot a linear model. So when you have all these data points in your graph, okay, you can obviously draw a plot. So you can have a line which passes through all of these points, right? Or not all, but passes through the points. Okay, and from this equation, you will use a linear regression equation called y equals to mx plus c. We all know that y equals to mx plus c is the line of the linear regression, or line of an equation of a line. I'm sorry. So it is a equation of a line where y is the dependent variable, which is called the price here. X is your mileage, which is the independent variable. This is your mileage. Okay, and c is the intercept, which we will understand in the next slides. What is the intercept? So intercept is basically the distance, okay, between 0 and the point where the line has touched. Let's look into this with an example. So as I said, y is the dependent variable here, x is the independent variable here, and c or b is the line where the line crosses the y-axis. It's also called the y-intercept. Okay, it is also called the y-intercept. Now with linear regression, we have something called the error term as well. So whenever you have a y equals to mx plus c or b1x plus b0 plus error. So error is something which is present in the data set, because obviously we know that there cannot be a model which is 100% accurate. So it should carry some sort of error with it. Okay, so when we say y equals to mx plus c or y equals to b1x plus b0, we also introduce something called the error term, and we will see what is this error term in the next diagram. Okay, so let's understand this with an example. Okay, so you have Costa's Pizza Parlor, okay, and students contribute the major amount of sales of that particular pizza parlor. Okay, and as you can see, the student population in thousands, so you have 2,000, 6,000, 8,000, 10,000, 12,000, and as and when the number of student increases, right, in that particular outlet, the quarterly sales also increases. Okay, so you can see a direct relationship between number of students and the quarterly sales. Okay, so it basically follows a linear relation. It basically follows a linear relation as and when your number of student increases. So if your number of students increases, right, your price or the quarterly sales will also increase. So you can see these points as and when the population of students is increasing, the sales is also increasing. Okay, so you have a linear relation. Okay, obviously when we create a linear relationship, we create a straight line, and we cannot create a line which joins points. Okay, this is what we have shown here, that you should have a linear line which passes through all these points, passes through these points. Okay, now in here, b1 is the slope of the regression line. This is called the slope of the regression line, and b0 is called the intercept, and E is the error. Let's understand this. Now, if you have a model which says, say, y equals to mx plus c, For now, don't consider the error. And if I say y equals to m is, say for example 5x plus c, it means the m value or the slope value or the beta 1 value. If you say y equals to b1x plus b0, in that case the b1 value, right, is called the slope. It means that with increase in the student population on thousands, uh, the increase in the sale is going to be $5,000. Okay, so if your sale, if your student increases by 1,000, then your sale will also increase by 5 times, right? If your number of students increases by 10, your sale will also increase by 10. So if in a particular outlet, say for example, on Jan 1st, you know that there are going to be, say, 10 students. Okay, on that particular day, there are going to be 10 students. Then you can automatically predict that if this increases by 2, if this increases by 2, so in the next year, on the same date, if it is 12, right, your sale, which was X, is also going to increase by 2 times, right? 2 times at that particular individual. Say, for example, it was 10 into X. So now it will become 12 into X, right? It will become 12 into X. So if your cell was 10 into X, now it will become 12 into X. So it is increasing in a proportion of the slope. Okay, we'll again show you the same thing now, but now try to understand what is intercept. Intercept is something which is present even if the value is 0, right? So if there is no student at all, if it is no student at all, if there are no student at all, we will at least have a quarterly sale of 60. This is what the intercept tells you. Let's understand this with another example. Say for example, if you have a cable TV at your home, right? If you have a cable TV at your home, and the cable TV operator will probably say, every channel will cost you 5 rupees. And if you want to have 100 channels, you have to pay 500 rupees. That's fine. Okay, we are willing to pay 500 rupees for 100 channels. Now he will say that even if you don't take any channels, the base price is going to be 200. So I will charge you 200 even if you have 0 channels. Even if you take 0 channels. So this 200, which is without any channels, is called the intercept. So intercept is something. Yeah, C is equals to 200 and slope is 5. Yes. So C is going to be, so when I say per channel, it's going to be 5 rupees, right? And the base is 200. Even if you don't take any channels, you have to pay me 200 rupees. So if you take 500 channels, it is going to be y equals to mx plus c. So your m is 5. With per channel increase, the price will also increase 5. So you have 5. If you take 100 channels, you have 100, which is x. X is the independent variable, which is channel, and c is your base fare. So all in all, you have to pay 700 rupees to that particular individual. And in next month, if you say, I am going to my native, I don't want your subscription of 100 channels, he will say, okay, no problem. You have to pay me 0 rupees for 100 channels because you are not taking any channels, right? So you'll pay 0 and then you will have to pay me 200 rupees. So your base fare is going to be, or your base price is going to be 200, even if you don't take any channels. Okay. So in the same way, quarterly pizza sales, you can say even if there are no student, okay, that particular outlet is going to sell $60 or 60 number of pizzas. Okay, whatever unit it is. Understood? Now, how linear regression works? Linear regression has something called the random error, okay, or we call it residuals as well. We call this random error as residuals, right? Now, what are residuals? Residuals is basically a difference between observed value of the dependent variable and the predicted value. Okay. See, for example, for now, just ignore this diagram. Say, for example, if I say, salary. If a particular individual says that, I have a target based salary, or I sell, insurance products, right? And based on that, my salary is different every month. Okay, it depends on number of insurance I have sold. So if I predict something and if I observe something, so if I have predicted, say I am the sales agent, I have predicted, in January, February, and March. In January, I am going to get, say, for example, 10,000 rupees as my salary. In February, 12,000, and in March, I'm going to get 15,000 because the year end for ITR is approaching, and we generally tend to buy, all this insurance at the end of the year, or probably just before we file our ITR, income tax return. And we observed that, my salary in January was 11,000. In February, it was 12,600. And in February, it was 13,500. So this is the residual. Residual is nothing but the difference between the observed value and the predicted value. So observed is 11,000, predictive is 10,000. So we have 1,000. This is the residual or the error in my prediction, right? 600 here and minus 1,500 here. So this is called the residual. So in here, when you see, this is the line which basically is the observed value, predicted value. Okay, this is my predicted value. This is what I have predicted. And this is my observed value. So the difference between observed and the predicted value. Okay, if you just draw a line. So this is going to be my error. This is my error. Right? This is going to be my error. Now with the mileage and price of a car, we can obviously observe that there is a difference between the observed value and the predicted value, just like the previous slide. I have to just change this slide, this line. Okay, so this is going to be my error, and with the pizza sales as well, we will have some error because we cannot have a single line which can pass through all the data points. Okay, so the residual is basically the difference between the observed value and the predicted value. Now, how can you evaluate a linear regression model? Okay, you can evaluate a linear regression model using the line of best fit. Okay, so if there are many points, say for example, there are many points like this. If you have 3 points, I can draw a line like this. I can draw a line like this. I can draw a line like this. But why have I drawn a line like this? And I'm saying this is the best fit line. We have to understand. So you can basically draw as many lines as possible, but there is going to be only one line which is the best fit. And how can we calculate that? So we have to find the best slope and the intercept that fits data points, and we have to minimize the residual error. So the error which we have calculated here, okay, this has to be the minimum. So you can obviously understand that if I, observe something which is exactly 11,000, in that case, my residual would have been 0. If I would have, predicted 12,000 instead of 12,600, my answer would have been, error would have been 0. If I have predicted something as 15,000 and observed value was also 15,000, in that case also my, residual would have been 0. So this is something which we can create using the best fit line. Obviously the error is not going to be 0, but we will try to make it as minimum as possible. To do that, we have, three data metrics. One is called the mean absolute error. The second is mean squared error, and the third is root mean squared error. Okay, very easy. No need to worry about it. Now let's look into the first one, which is mean absolute error. Mean absolute error is basically the average absolute difference between actual and the predicted values. Okay, it is going to be the average of the absolute difference between actual and the predicted value. And what are the characteristics of this metric? It is neutral to outliers, right? Error is in same units as that of the data point. Okay, let's see this with an example. With mean squared error, what we have done is we have just removed this modulus, right, and changed this to a square. So that's why we have mean squared error. Mean absolute error because you are taking the absolute value, and mean squared error because you are taking the square of the values. Mean square error is the average square difference between actual and predicted values, right? It is the average square distance between actual and the predicted value. Now, what are the characteristics? It accounts impact of outliers. Okay, if you have an outlier, we will look into that. Okay, don't worry about it. If you have an outlier, it will impact that. And error is not in the same unit as that of the data point. Obviously, when we are squaring the data, say for example, if you have you are calculating say cc, right, 150 cc is the volume of my bottle, and you have created a regression line which basically predicts, that my volume is going to be 150 cc. But when you observe this data, some has 151, some has 153, some has 148, some has 147, right? And these are the difference. So here the difference is 3, here the difference is 1, right? Here the difference is -2, here it is -3, and so on. So if you square these values, if you have 3 cc, and if you square this 3 cc, you will basically have cc square, right? You have cc square, and which is not the same unit as the data point. So data point is cc, but your mean squared error is cc square. So the unit has changed. Okay. Now to counter this, we have a root mean squared error. The only difference between the previous one and the next one is we have a root under. With this root under, what we are doing is at the end, when you have cc square and you're performing root under, it again changes to cc, right? In that case, your problem is solved, that the error is same as that of the data point. And it also impacts the outliers. What is the outlier here? Say for example, if my volume is 150 cc, which is what I am, observing, predicting, right? I have predicted that the volume of the bottle is 150 cc, and you all of a sudden got an observation that it is 200 cc. So all these previous points are, either 2 distance away or 1 distance away or 3 cc away or 4 cc away. Out of a sudden, you have a data point which is 50 cc away. And if you plot this, it will probably be here, right? It will probably be here, 200 cc. It will probably be here. So you see all these data points which are present here, but all of a sudden there is one data point which is present at the outside, right? In that case, this is an outlier. And to counter the impact of the outlier, what we do is whenever we perform a square, right, square of 50 cc, it will change to 2500 cc, right, which is a very big amount, and which is a very big amount, and the volume is such that it will impact the outlier. So whenever you create, the root mean squared error, and if you see this value is, very high, you'll understand that there is the impact of the outlier. Okay, we'll come to this again. Now, with Costa Pizza's sales, you can see the student population of 2, 6, 8, 10, 12, and so on. And you have the quarterly sales, which is 58, 105, and 88 and 118 and so on, right? And then you have this. So this is what you have observed, and this is what we have predicted, that it is going to be 70 and 90 and 100 and 100 or 110 and so on. So now the difference between your observed, and the predicted value is going to be minus 12, right? Just want to show you the, yeah. So actual and the predicted value is minus 12. So this is your actual sales, and this is what you predicted, right? So the difference between actual and predicted, A minus P, is this. So 58 minus 70 is minus 12, 105 minus 19 is 15, right? 88 minus 100 is minus 12, and so on. And what you have done is you have taken the absolute value here, A minus P, and then absolute. With absolute value, you will not have the negative sign. So absolute of minus 12 will be 12. Absolute of 15 will be 15. Absolute of minus 12 is going to be 12, and so on. So A minus P absolute is this. And in here, what you have done is you have performed the square, A minus P square. So 12 square is 144, 15 square is 225, minus 12 square is 144, and so on, right? And if you try to create the, and if you calculate this using the formulas MAE and MSE and RMSE, you will basically find this here, right? So if you want to find MAE, what you will do? If you want to find MAE, what you'll do? You'll basically add them up, right? Mean absolute error, you will basically add them up and you divide it by the number of data, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you have 10 data. So if you add them up, right, and divide it by 10, sorry, add them up and divide by 10, you will get a 10. Okay, so it will basically add up to 100, 100 divided by 10. So this is basically 100 divided by 10, right? And likewise, if you try to calculate this, where you sum them all them up, right, and divide it by 10, you will get 1310. So it will be 1310 divided by 10, right? And if you just do a under root of this value, so you'll get 11.31. So if you do 131 root under of 131, you will get 11.45. So this is the MAE, you have MSE, and you have RMSE. So this is the calculation. So for this particular data set, you have 10 as the MAE, 131 as the MSE, and 11.45 as the RMSE. Got it? This is now calculated. Now, with the introduction of or the change of certain values, you see, they have introduced some outliers in the data. You have introduced some outliers in data. You see, the difference is huge, 167 and 120. Right? The difference is 47, and 47 square is going to be 12209. You have 260 and 165. The difference is 95, and 95 square is 9025. Right? And with the introduction of these outliers, with the introduction of 1, 2, 3, or some of these outliers, what you can see is that difference is huge. See, the mean absolute error is 24 and the root mean squared error is 34.5. So the difference is 14.5. But in the previous one, when there was no outlier, you can see as such, there is no such outlier in the data. Okay. The difference is going to be 11.45 only. Sorry, 1.45 only. So with the introduction of outliers, the difference between the mean absolute error and the root mean absolute error is large, right? So it means that root mean squared error is more powerful, right? Whenever there is a large error, because the root mean squared error gives high weightage to large errors. So all these errors, whenever they are squaring it, whenever we are squaring it, it gives high importance to these outliers. And as a result of that, root mean squared error value has changed significantly. So root mean squared error is more powerful when large error occur. Okay, you will be asked this question in interview, that which metric in linear regression is the most powerful if you have outliers. So you have to answer it with root mean squared error. And if someone asks you a counter question why, then you have to tell them that since we are squaring it, right, we are inflating these large values, and when we take a square root, there's a significant difference between the mean absolute error and the root mean squared error. Any question till now? Or you want to revisit any topic? Do let me know. All clear? Okay, great. Residual graph explanation. Okay. Okay. Okay, let's look into this with an example. Just give me a second. Let's say I have some predicted value and some observed value. Predicted value is something which my model has predicted. Okay, say for example, the number of students in my class. Okay, number of students in my class. Right? Say for example, if I am taking a session on Jan 1 and Jan 2 and Jan 3 and Jan 4. Right? And my model has predicted that 10 people are going to join. Here 8 people are going to join, 12 people are going to join, and 15 people are going to join. But when I observed it, right, and when I this is what I predicted in December. Say for example, I predicted in December that 10 people are going to join on 1st of January. But I observed that there are only 7 folks who have joined. In here 12 folks have joined, 15, and here 10. Now what I said is, it is the difference between the observed value and the predicted value. So now you know that what is your observed value and what is the predicted value. So observed minus your predicted value, right? Observed value is -3. Observed minus predicted is -3. Here it is 4, it is 3, and here it is -5. So this is your table. Now if so this is called error or residual, right? And if I want to plot this over a graph, if I want to plot this over a graph, so you have Jan 1, Jan 2, Jan 3, and you have Jan 4, right? I want to plot this over graph, and say for example, this is 5, 10, 15, this is 20. So this is my y-axis, which has number of students, and this is my day. Now, if I plot this, what you have got is you have, say for example, observed value, which is 7, right? Your observed value is 7. So 7 will be somewhere around here, just above 5. You have 7. On Jan 2, you have 12. So 12 is going to be here. This is 12. In Jan 3, you have 15. So 15 is going to be here. And Jan 4th, you have 10, right? So Jan 10 is going to be same here. So this is my observed value. And say, for example, if I draw a line, which passes through these points. So this is actually the residual. So this is my predicted. And these points are my observed points. These are my observed points. The difference between this and this is my residual. So in here, we have calculated the residual is -3. Right? Here, say, for example, the residual is 4. Right? And here it is 3. And here it is, say, -5. So this is my residual. You understand the graph now? These are my residuals. Great. Now these all residuals are -3, 4, 3, and -5, right? These are my residuals. These are my residuals. And you can say that, okay, sir, I want to calculate the mean squared error. Now we know that mean square error is number of terms, and then you sum all these terms with absolute values, right? So you will have something called mod of -3 plus mod of 4 plus mod of 3 plus mod of 5 -5. All we know that, mod of -3 is going to be 3. So with mod, everything changes to a plus value. So 3 plus 4 plus 3 plus 5. And we have number of terms n is equals to 4 here because we have only 4 terms for 4 days, right? So 1 by 4, and you have 3 plus 4, 7, 7 plus 3, 10, and 15. So 15 by 4. So my mean absolute error is going to be 3.75. I hope we all understand now what is mean absolute error. Now, instead of that, if I want to calculate mean squared error, what we'll do is instead of this mod, I will change this to square values. Square values. So now this will change to 9 plus 16 plus 9 plus 15. Right? So you have 9 plus 16, 25 plus 25, 50 and 59. So you have 59 divided by 4, right? Which comes somewhere around 14 point something, right? 14 point something. Say for example, I take 14.9. So you see the mean absolute error is 3.75 and the mean squared error is going to be 14.9. And if you want to calculate, so this is mean squared error. And if you want to calculate the root mean squared error, you just perform a root under, right? You perform a root under. So root under of 14.9 is going to be 3 point some values, 3.8 or something, right? 16 root is 4. Yeah, 3.8 something, right? So you see the difference between the mean absolute error, which is 3.75, and root mean squared error, which is very less. So you can understand from this difference that you have very less, outliers, or you have insignificant number of outliers in your data. Had the observed value been, say, 17, right? In that case, the predicted value would have changed to -7. And in case -7 whole square is 49, and if you have 49 here, you can understand it will cross 4. So it would have been 4.2 or 4.3. So as and when the difference between the mean absolute error and the root mean squared error is wider, okay, there is a chance of outlier in your data. I hope you understand now. Right? We'll move on to the next one. Now there are certain important assumptions, right? We have to understand for any linear regression. So there are 4 assumptions. The first is there's a linear relation between independent and the dependent variables. When you see linear, it means either with the change of independent variable, the dependent variable will come down or go up. Okay, we'll understand what is the linear relation. We'll have we should never have a multi-collinearity between independent variables. Okay, if there are 2 independent variables or 3 independent variables, there should not be any multi-collinearity. The residuals should be homoscedastic. Okay, we will understand what is homoscedastic, and residuals are normally distributed. Okay, residuals or errors should be normally distributed. Let's understand what is the first one, which is linear relation. When I say linear relation, it means that the data points which are present here should have a linear relationship, right? They should be linear. So the points should, be ideally distributed around these lines. All these points, whatever points we will have in the independent variable related to the dependent variable should be present, in a linear fashion. Okay, if it is not linear, okay, if the data point is not linear, in that case we will not be able to capture the information. Okay, so take this example where I have points like this, right? And if I just create a linear line, okay, and all these points are equidistant, or even if they are not equidistant, they are close to this best fit line. Okay, and they carry a linear relation between the independent and the dependent variable. But in the other scenario, if we have a data point like this, right, and if we try to go through all these points, so this is not a linear relation, this is a non-linear relation. So obviously you understand now that if we can draw a line, which passes through these points, okay, we will have a linear relation. But if we cannot draw a point, right, in that case it is a non-linear relation. We'll understand this with examples as well. Next is multi-collinearity, right? Independent explanatory variables are highly positively correlated with one another. Highly correlated independent variables explain the same variance about dependent variable, thus introducing redundancy. For example, if I have something to predict weather, right? To predict weather, you have independent variables like humidity, you have rainfall, you have temperature, and you have, say, for example, the last one, average temperature. Okay, these are the four independent variables, and this is the dependent variable because you want to predict this. Now, we all know that temperature and average temperature are highly correlated. It means if the temperature goes up, your average temperature will also go up, right? So the independent variables which are present here should not be positively correlated with each other. Understood? They should not be positively correlated with each other. So if they are positively correlated, we have to drop one and take only one into consideration. Because if they carry the same meaning, what is the point of taking both of them, right? And making our model complex. Okay, so if we take the same thing, right? Say for example, if we want to create a cricket team, we always want to make sure that, this cricket team is much diverse. Someone can bat at number 2 and number 3 and number 4, right? If there are two individuals who are very good at batting at number 2, right? And what's the point of keeping both of them in the team? Because if someone plays in the position number 3 or batsman number 3 as batsman 3, he will not be able to perform because I'm taking just assumption, okay? He's not, good at any other position apart from number 2, right? So we will drop one individual and take only one individual in the number 2 position, right? So this is a multi-collinearity. So the independent features should not be positively correlated because they explain the same variance about the data. Now let's take the below example. Okay, this is with the multi-collinearity, the second point here. If you have a car, you have a bike and you have certain specification that has 5 gears and it has 883 cc engine, and it has a mileage of 15 kilometers per hour, and then you have another variable or column which says 883 cc and 5 gears. So obviously you know that there are two columns which are redundant and they have the same meaning, right? And if I change this to by dropping these two values at the right hand side, it will basically will not have any issue with the model, right? Because these two individuals are talking about the same thing. Maybe they are looking different, but they are talking about the same thing. So there is a multi-collinearity in the data. Okay, so we should drop these type of columns, and when we drop this type of columns, we have 3 individual columns which explains the same thing about this bike. Okay, now multi-collinearity into action. So whenever you have 5 or 6 variables and you plot a correlation matrix is something which gives you what is the correlation between x1 and x2. The higher the correlation, the better the correlation value will be. Say for example, humidity and say temperature, right? If it has a relation of 0.9, it means that they are very highly correlated. If they have a value of say 0.5, it means they are less correlated. If it has a value of 0, it means they are not related at all. The sales of umbrella in Africa and the temperature in India is not correlated, right? So they will have a correlation value of 0. So whenever you have a correlation value which is very high, right, which is very high, in that case we have to remove it. Now x1 and x3, if you have 10 variables, x1 up until x10, you have x1, x2, x3, then x6, x7, x8, x9 and 10. Okay, so you have 10 variables here, and you can see x1 and x3 are having a correlation of 0.983. It means x1 and x3 both tells you the same thing. It both tells you the same thing. So what should you do? You can keep x1 and x3. If you keep x1 and x3 into your model, it might not add any extra value, right? It will not add any extra value. So you have to drop one of them. So values of correlation matrix are shown in here with the correlation matrix here. In the example, 0.989 indicates a very positive correlation between x1 and x3. x1 and x3. Okay. Now, what is the assumption number 3? Assumption number 3 said the errors are homoscedastic. Okay, the residuals are homoscedastic. What is homoscedastic? Homo means equal, and cedastic means implies dispersion, right? The data should ideally be very equally distributed along the regression line. So it means that ideally, if you draw something like this, if you have a regression like this, your points should be equally distributed, right? It should be equally distributed. So the dispersion of the data along the sides of the line should be homogeneous. You understood? So if you have a plot like this, your regression line should ideally go like this. Okay, it should ideally go like this. This is homoscedastic. Now, when I say errors are homoscedastic, it means the spread of residual values is constant as we move along the x-axis. So obviously, if you have a regression line, okay, the errors which you see here, these are the points, right? So the difference between the observed value and the predicted value is called error. So these errors, right? These errors should be constant, right? The spread should be constant. It means you should have a dispersion which is equal. Okay, and we'll look into this with practical examples as well. What is heteroscedastic? The difference of homoscedastic, right? Heteroscedastic. It means that as and when the regression the variation effect increases, right, with the increase in the value. So as and when the spread of the residual value increases, as we move to the x-axis, it is called the heteroscedastic data. So it should ideally not be like this, right? You should not have data points which increases over time. The dispersion increases over time. You see, the dispersion is increasing over time. But in the previous one, you have dispersion which is equal. The dispersion is equal. Okay, so what will happen if the residuals are homoscedastic? The family income versus money spent on luxury. So for example, right, bigger residuals imply greater error in prediction. So if you have if you have more difference between the observed value and the predicted value, it will mean that there is a huge error in your model. If you have a huge error in your model, your regression model will not be good, right? So we have to make sure that we understand all this concept. Okay, the fourth one is the error should be normally distributed. The error should be normally distributed. We all know that when we have a homoscedastic data, right, and we have created a regression line at the middle, right, and if we draw a line, okay, this data is normally distributed. The residuals in both the side of the line is normally distributed. So this is a normal distribution. We have seen this in statistics that whenever we have a bell curve, right, it is a normal distribution. So the error should be normally distributed and it should follow a normal distribution pattern. Okay, if you want to see, you can see here also that even if you draw a line anywhere, right, the data is normally distributed. Okay, you can draw anywhere, the data will be normally distributed. Okay, if the data follow a curved pattern, what will happen is, if you draw a line, if you draw a line, what happens is that here the difference between the observed value and the predicted value is very high. Here it is very low, right? Here it is again low, but these points are having, these are low, but these points are having high error. This will introduce bias in your data. So it means that as and when, say for example, mileage and your price of the car, right? Mileage and price of your car. So as and when the mileage increases, it says that your mileage decreases. So this is obviously less mileage, right? So it says when your mileage decreases, your car price will also increase if it is of the same brand, right? Obviously, this is not true. As and when the mileage decreases, your um, price of the car for a second-hand car will also decrease if it is of the same brand. Okay, so this introduces a bias in the data. So you should always have data sets which are having a normally distributed error. Right? For large samples, residual.
So,
yeah.
What do you mean by bias actually?
Bias in the data is something. So when we talk about bias variance trade-off, I can give you a better example. But for now, understand that bias in the data is something which introduces abnormality in the data. Okay. So for example, if you say I have a standard deviation of 2 cc when I have a volume of 150 cc in my manufacturing plant. But all of a sudden, if you see that at a higher temperature, the volume has increased to 167 and 170. It means that you are introducing bias um, in your data. With increase in temperature, the bias is also increasing. Why? Because it is not following the pattern in the data set.
Okay, sir.
Okay. I can show you with a better example. Let me. Okay, let me show you this with a Jupyter notebook. Okay. So for now, bias is something which is an inclination towards um, an incorrect prediction. Now, with large samples, residuals may follow any pattern or biasness, but still linear regression can be performed. So normality in the data is the least important assumption. Obviously, it is important, but normality is the least important assumption as of now for linear regression. Okay, as I said, we have 4 assumptions. The last one, which is residuals are normally distributed, is the least important. Okay, so we'll look into a case study of the data. Okay. So you have to take a bicycle ride in Washington, D.C. Okay. Now, bike sharing systems are a means of renting bicycles throughout Washington, D.C. Analysts are asked to combine historical usage patterns with weather data in order to forecast bike rental demand in capital bike share program in Washington, D.C. So you are being asked to create a regression model to find out how many bikes are going to be rented on a particular day. Okay, let's look into the data which has been shared to you by the company. So the data which has been shared to you has date, time. Okay, what is the season, what is the weather, and whether it is working day or if there is any humidity, right? And the total rentals, right? So obviously you are going to predict what is the total rental. So can someone tell me what is the dependent variable here? Yeah, total rental is the dependent variable because we are going to predict how many people are going to ride the bikes, right? How many people are going to rent the bike. And the independent variables are date time, season, weather, working day, and humidity. Right? So the data will look something like this. If you have a CSV file, you have a date time, you have season, holiday or a working day, right? Weather, temperature, and the count of rent of bicycle, right? You will perform some sort of analysis on top of it, right? You will look into the statistical analysis of the data. Just to show you this in a slide, we'll do this similar type of example in Jupyter Notebook. So we'll try to find out if there is any, correlated value which we have seen that the average temperature is highly correlated with the temperature, right? The P is 0.9845. So you can reject one of these values, either average temperature or the temperature. Again, count is highly correlated to registered, right? So you can reject any one of them. So you can reject registered for your analysis. Okay.
Sir, sorry to interrupt. We are saying we are rejecting a few independent variables, right? If correlation exists. So just like whether we do it manually or algorithms will take care of these things.
Generally, we program it in such a way that algorithms will take care of it. But for your analysis, we have to also understand if we want to do this manually. Okay.
Okay.
So how can we do it? How can we analyze? Obviously, we can program it whether if any correlation value is greater than 0.9, just simply ignore it, right? So this is how we generally do in production. But for our analysis now, we will do it manually so that we can get a flavor of how this is done or how it was done when a statistician used to do it.
Okay, sir. Thank you.
Right. Okay. And then you will plot this data set. So the average temperature in the area throughout the year is around 0 to 40 degrees centigrade. Okay. So this is what you have understood from the data. So you have created a distribution between the frequency of, the rental of bikes and the distribution of temperature. And then analyze the number of casual rentals based on holiday and weather. So what is the weather and how many casual rentals we are getting. So we can understand that bar plot illustrates no casual riders during holidays, during extreme weather conditions. Obviously, when there is extreme weather condition, we are not supposed to ride bikes, right? We'll probably take an Uber or a car, or we'll stay at home, right? So this is what we are analyzing through the data. So this is for your exploratory data analysis. Next is you analyze the registered and the casual rentals based on year and month, right? And you can see that over the year, how many bike rentals are there. Plot illustrates that registered and casual rental are steadily increasing, right? It increases and then it decreases. Okay, so we can see that in the left hand side, you have registered users, right, which are steadily increasing, and you have casual renters, which increases and decreases based on the months, right, or based on the temperature as well. Next, we analyze the casual rental based on the time of the day. So at what time, you see number of bike rentals. Registered riders are least active during Saturdays and Sundays and during heavy showers. Obviously, if they are registered, they are using it for their office or schools or colleges, and they are least active during Saturdays and Sundays. Then we want to find out the relationship between the different features through a heat map, right? Humidity and number of casual riders are negatively correlated, implying drop in riders when humidity is high. So whenever the humidity is very high, right, we prefer not to go out. It's very sweaty. So that's why the number of riders are also decreasing, right? So if you look into humidity and the number of riders, what you can see that they are very negatively correlated. Okay, now comes the regression part. We will perform some linear regression on the bike share. And based on this, we manually have calculated, there are 4 features which we think is going to be ideal for our analysis: temperature, season, weather, and humidity. These are the 4 independent variables which we have chosen, right? We have chosen from the list of independent variables. We'll come to this, don't worry about it. So what you create a X variable which has all the feature columns, and you have the Y variable which is the total number of bikes, and you fit this to a linear regression model, and from here you can find the intercept. Intercept says that even if there is no schools and colleges, you have 159 bikes which is going to be rented, and then you have the individual slope of all these 4 features, which is 7.86, 22.53, 6.67, and minus 3.11. What it means is, if you carefully observe this, it means that 1 unit increase in temperature is associated with a rental increase of 7.86 bikes. So if there is 1 degree increase in temperature, right, 1 degree increase in temperature, there is going to be 7.86 more bikes which are going to be rented, right? 1 unit increase in season, right? As the season changes, 22.53 bikes are 22.53 bikes are getting rented. Again, once 1 unit of weather changes, or once the weather changes, you have 6.67 bikes which are getting rented. And as and when the humidity increases by 1, the number of bikes which are rented are decreasing by 3.11. Right? Hope you all understand. With negative we have decrease, and with positive we have increase. Don't worry about the unit here. Okay, it means that with increase in humidity, the rental decreases by 3.12. Obviously, when the humidity increases, we are not supposed to, we don't prefer going out on a bike. Right?
Just a question here. A temperature increase, weather increase, fine, but season normally it changes. So increase, how does it exactly indicate here? I mean, which season it is?
Yes. So in here, if you see the season, right, the season is 1. So there was 3 or 4 seasons, right? Okay. It is set to a categorical number.
Understood.
Okay, so as and when the season changes, so on an average, 22 bikes are getting rented, more rented.
Understood. Got it. Thank you.
Yeah. Now from here, what we can do is we discuss some terminologies associated with error. One is the sum squared due to regression, which explains the deviation from the mean. We have sum squared due to error, which unexplained deviation from the mean. And we have sum squared total, which is the sum of SSR and SSE. Right? What is this? If you want to understand what is the SSR, so let's understand sum square due to regression. Okay. Now the intuition behind this is, at 38 degrees centigrade on a particular day, we predicted 260 ice creams to be sold, which is higher than the mean Y. Okay. So your mean is here. This is your mean Y dash. And you have predicted something which is more than your mean. Right? You have predicted 260, but in actual it was say somewhere around 220 or something, right? On 38 degrees centigrade. This deviation collectively for all predictions is termed as SSR, sum square due to regression, or explained sum of square. So you know that there is some deviation, right, from your mean value. From your mean value, when I say mean value, it's actually the mean of all these points. Okay, all these blue points. You are creating a mean value, and you know that this is an explained value, right? That my average was somewhere around say 200 and I am getting 260 and the difference is 60. I know this is getting explained to us, right? And we call it SSR, sum square due to regression. We accept this deviation to calculate the R square value. We'll calculate the R square value next. Okay. So this is your sum squared or due to regression. Next is sum square due to error. Right. Now you have, this is your mean line. Try to understand. 1 second. Yeah. So this is your mean line. This is your mean line. And this is your regression line. Right. Now at 38 degrees centigrade on a particular day, actual number of ice cream sold was 300, which is higher than our prediction, which is 260. So the deviation or difference is called sum squared error. This deviation is unexpected or unexplained from the mean, right? It is the difference between the regression line, right? It is the difference between the regression line, right? This is your regression line and the point. So this is called the sum squared error and it is unexplained, right? We don't know. This is unexplained. So the inference is that this difference can't be explained by the difference in independent variable. We want this as small as possible. So obviously, whenever we create a regression line, we want all our points to be as near as possible, right? So that it passes through all the points. If we have points like this, this, and this, obviously the error will increase. The error will increase, and this will be hard to explain the difference. Right, so this is called the SSE, sum squared error. So now you understand that the difference between this point and this point is called the SSR, and the difference between this point and this point is called SSE. Right, nothing else. This SSR is explained. This is explained. We know that this is the mean and this is our own regression line. Okay, we know this also and this also. So this is explained. This regression line is what the model is creating, right? This line is the model is creating this line, but this point has a difference between the regression line and the error and the actual point. So this is called the SSE, a sum squared error, which is unexplained. Right, and we want this as small as possible. We want this as small. We want points like this, right? We don't want point like this. So ideally, we should have these points or the error between these points as low as possible. Okay, and now SST is basically the sum square total is basically the sum of these two values, right? You can see SST is equals to SSE plus SSR. So this is your SST, SSE plus SSR. So the total sum square total is deviation of the actual data point from mean, right? So this is your mean. This is your mean. This is your mean. And the distance from the mean to the point is called the SST. This is called the SST. Now, what is R squared? In regression, we don't have anything called accuracy, or a precision or a recall or a confusion matrix. We don't have something like that. In regression, we have something called the R squared value. It is the most popular metric to measure the performance of a regression model. And it tells about the variability or difference in Y variable explained by difference in the X variable. Okay, so don't worry about the definition now. Just now try to understand that R square is nothing but the ratio of SSR by SST. Okay, it is the ratio of SSR by SST. Or we can alternatively say it is 1 minus SSE by SST. So SST should be at the denominator, SSR divided by SST. This is our R square. Okay, or we can say 1 minus SSE by SST. Because ultimately, if we do SST minus SSE, right, by SST, we will eventually get SSR. Okay, so R square is the ratio of SSR and SST. Now this is called the coefficient of determination. This is called the coefficient of determination. R square is the square of correlation coefficient between dependent and the independent variables, and it also called the degree of association between X and Y. The better the R square, the better the model is. Okay, let's look into it. Say for example, if you have a R square value, which is 0.81, okay, it means that 0.9 R is 0.9. So 0.9 is 90%. So 90% change in Y is known to X and vice versa. So for example, if we have a linear regression with say mileage and price, so obviously this is the Y variable and this is the X variable. And if you have a R value of say 0.95, which is 95%, right? It means that 95% of the change in price, right, can be governed by mileage or can be described by mileage. So instead of if it was say 65%, so we understand that if the association is only 65%, the model is very weak, right? It's not that strong. So the rest of the 35% association between the mileage and the price is unknown. We don't know how this association is, right? And that is why we can say that this model is not that great. 65% is not that great. So coming back to our example, when I say 0.81, R is obviously root under of 0.81. So it means 90% change in Y is known to X and vice versa. Or alternatively, we can say that remaining 10% association between X and Y is unknown. And this is why X can't explain remaining 19% difference in SSE, right? The rest of the 19%. Understood? Now we come to the next part, which is the adjusted R square. So we have R squared here. We have the adjusted R square. Adjusted R square is more powerful metric than the R square to measure the linear regression model. Right? Adjusted R square is more powerful than the R square to measure the linear regression model. It measures the proportion of variation explained by only those independent variables that really help in explaining the dependent variable. It penalizes you for adding independent variables that do not help in predicting the dependent variable. Okay. Say for example, you have humidity, you have temperature, and you have season. And you have your adjusted R square. Okay, you have adjusted R square. So now with humidity, temperature, and season, if your adjusted R square came out to be, say, for example, 0.9, right? And you said 9.9 is what I'm not looking for. I'm looking for something better than 0.9. And you introduced one more, feature. Say, for example, you introduced average temperature. Just an example. And with that, what happened is your adjusted R square changed to 0.87. It means that with the introduction of this new independent variable, the model has penalized it. And due to that penalization, what has happened is the the value has reduced by 3%. So obviously you understood that this independent variable is of no use for me. So it measures the proportion of variation explained by only those independent variables that really help. So these are the ones which really help explaining the.
So can you explain once again?
Yeah, sure. So it means that if for example, if you in the first scenario, right, you took only 3 columns: humidity, temperature, and season, in order to predict your price. And when you created this model using, say, the linear regression model, your R square value came to be 0.9. Okay. And then next scenario, what you did is you wanted to, increase your model accuracy. To do that, what you did is you introduced a new column called A temperature, or average temperature, and then humidity as well, and temperature and season. And once you added A temperature, the model accuracy actually reduced to or decreased to 0.87. It means that due to the addition of A temperature or average temperature, your model is not behaving correctly. So you have to avoid this variable because it has penalized the model, because A temperature does not really help in predicting the price. Understood? So it penalizes you for adding independent variable that do not help in predicting the dependent variable.
But sir, sometimes it's important, right, to take those variables into account. Like for now, A temperature is not that important, but sometimes we need more factors to evaluate our model, and our accuracy decreases with that. But we can't miss those factors. Then what we have
Right.
to do?
So in that case, we have a tolerance level. Okay. So we have a tolerance level that, even if we are introducing a new column, and if we see that it is not significantly changing. So for example, from 0.9 it changes to 0.65, you know that something is very wrong with that particular column. But for example, 0.9 changes to 0.89 or 0.86 or 0.87, based on your scenario or your business case, it is completely okay to take that. Ideally, I would have changed this to 0.67. In that case, it would be easy for me to explain. But again, it depends on your domain, business domain as well. Okay, just like we have alpha level in statistics of 0.95 confidence, you can have 0.9 confidence as well. Okay, more to that when we do on in our practical classes.
Okay, sir.
Right. See an example here. What happened is you have variable 1. When you have only one variable and you created a model, your R squared value was 67.5. Your R squared value was 67.5, and your adjusted R square was 67.1. Right? When you introduced a new variable with 2 variables, okay, say for example, it was only humidity. With humidity, your R square value was 67.5 and adjusted R square was 67.1. When you introduce, say, humidity plus temperature, your R squared value increased to 85.9. That's good. And your adjusted R square value is 84.2. That's good, right? And when you introduce the third variable, say for example, humidity, temperature, and say season. With that, your R square value increased, right? But your adjusted R square actually decreased. So adding second variable, adjusted R square has increased along with R square because the variable has less impact on the dependent variable. But third variable increased R square and reduced R square implies that the variable is not impactful at all. Right? So when you see your R square value and adjusted R square value both has increased, it means that it has a real impact on the dependent variable. Your dependent variable here is the number of bikes or count of bikes for rental. But when you introduce something where the R square value increases, but the adjusted R square actually decreases, in that case, you can say that it is not impactful. And this method is used in order to, perform variable selection. Okay, this is done to perform variable selection. Now, what is the difference between R square and adjusted R square? Very important question. If you go for a finance-based company, you are basically asked this type of questions. You should be able to answer it. R square and adjusted R square. First, R square can be 0. Your R square value can be 0. Adjusted R square can be negative. Every time an independent variable is added to our model, the R square increases even if the independent variable is insignificant. R square never decreases. So as and when you add more variables, so if you add more variables, so if it is 4, for example, here, right, there is four variables here, your R square will probably increase. It will be say 90. Okay, and based on whether it is impactful or not, your R squared value will either increase or decrease. Say for example, if it is impactful, it will be, say for example, 83. If it is not impactful, it will go to 79. Right? Understood my point? So what we are trying to say is R square value will increase even if it is, that particular independent variable is significant or insignificant. Adjusted R square only increases when independent variable is significant and affects the dependent variable. Okay. So that's what we have for linear regression. In the next class, we will look into the practical scenario, and don't worry about anything. I will share this slide deck with you, and we have, a very interactive Jupyter notebook, which we'll go through again just to understand, how linear regression can be used. We'll again look into what is a linear regression so that you have a bigger picture in mind. Where is linear regression used? What are the different case studies? What are the different types of linear regression, right? We will also look into something which is, complexity of a model. Someone asked me about bias. I will be able to better answer it using a diagram here, right? A bias variance trade-off. We will look into what is the error in the amount of data. Should we have more data in order to have a better model? And then we will look into what is the training and testing split of the data, and then we'll start with the linear regression model. Okay. Before that, if you have any question, do let me know. We will perform our exploratory data analysis as well. As I said, EDA, I don't want to take separate classes for EDA because it unnecessarily, we have to repeat the same thing again and again. And once we go through machine learning, we tend to forget what we have done in the previous class. So it's better to relate it with the use case. Okay, any question? If you have any question, do let me know. Okay. If you have any question, do let me know. Drop me a WhatsApp chat and I will get back to you. Sorry, I couldn't give you one more break. Ideally, it was asked to give 2 breaks. But no problem. We'll meet tomorrow again. 1 second. Can you share it? Cheat sheet if you have prepared? Yes, statistics cheat sheet is still into progress. Okay, I don't have here. Okay, I will share the cheat sheet with you probably next week. Didn't get time this week to create it. But if you have any other question, do let me know. With statistics, we will start, MCQ questions every day once we are at the mid of, machine learning, so that you can also relate how statistics and machine learning is hand in hand.